Hello and welcome. In the previous lectures, we were talking about double sideband amplitude modulation with carrier. Just a short recap of what was happening there. We were modulating a message signal MT with a carrier signal AC cos omega ct, and in the modulated signal there were both upper sidebands, lower sidebands and carrier components. In today's lecture, we will mainly focus on double sideband suppressed carrier, where there will be both upper and lower sidebands, but carrier component will be suppressed. Before starting our discussion in detail, let's get some quick overview of what will be happening in Dsbsc. First of all, as I have mentioned, the carrier component will be suppressed and not transmitted. As you can remember from the Dsbc amplitude modulation, a majority portion of power was consumed by the carrier component. That's why the efficiency was low. But as in this system, carrier component will be suppressed, so the power efficiency will be increased. Next up, bandwidth requirement. Bandwidth requirement is basically same as Dsbc. In this case also, the bandwidth requirement is twice of the message signal. And another thing, unlike Dsbc, in the case of Dsbsc or double sideband suppressed carrier, envelope detection cannot be used. So let's dive into the details. First of all, the equation of Dsbsc signal. In the case of Dsbc signal, there were two components. One was carrier component, AC cos omega ct, and one was modulated carrier or MT cos omega ct. But in the case of Dsbsc signal, as you can see, there are no carrier components and only the modulated carrier is present. That's why we call it Dsbsc or double sideband suppressed carrier, as the carrier is omitted. So how we can produce this Dsbsc signal? The first approach is very straightforward. As you can see from the equation that this is simply the multiplication of the message and the carrier, right? So we can use a multiplier block, and two inputs will be the modulating signal MT and the carrier signal cos omega ct. As you can see, there are no carrier amplitude here. That means the amplitude is by default 1. If you use any other amplitude, that is not a problem. The structure will be similar. So this is our modulated signal MT cos omega ct. As you can remember from the previous discussion on Dsbc, there were 3 steps of drawing a Dsbc signal. In the case of Dsbsc, the first step is not required. What you will need to do is draw the message signal, draw the reflection of the message signal, and the step 2 or the last step is insert the high frequency carrier in between. Straightforward. Okay, now let's analyze it in frequency domain. Let's assume this is the frequency spectrum of this time domain signal. So when we are modulating this signal, the equation is MT cos omega ct. As you can remember from the Fourier transform that when a signal is modulated with cos carrier, the spectrum of the signal is shifted to positive and negative values of the carrier frequency. The carrier frequency is omega c. So in omega domain, this spectrum will be shifted to omega c center frequency and minus omega c center frequency. And as you can remember, the amplitude will now be half of the original amplitude. As you can see in this case, the amplitude was 2A, and in the modulated signal, the amplitude of each of these spectrums is A. Of course, there are both upper sidebands and lower sidebands. This and this part makes up the upper sideband, and this part makes up the lower sideband. And you can see the message bandwidth is actually 2 pi b, but the modulated bandwidth is actually 4 pi b, double of the original message. Now, how we can demodulate this signal? The demodulation is also the same process of modulation. In the case of demodulation, the first input is the modulated signal MT cos omega ct, and another input is the carrier itself cos omega ct. So these two signals are multiplied and then passed through a low pass filter. I have previously mentioned, whenever you are designing a demodulator circuit, you will need a low pass filter. When you are designing a modulator circuit, you may need a band pass filter. So let's see what are happening in terms of mathematical equations. So our ET signal is the multiplication of the modulated signal and the carrier signal. So this is our modulated signal multiplied the carrier signal. As the modulated signal is MT cos omega ct, the multiplication will be MT into cos squared omega ct. As you all know, we can use the formula of 2 cos square omega ct here, and the formula is 1 plus cos 2 omega ct. So the result is half empty plus half empty cos 2 omega ct. There are two parts. The one is message, another one is the modulated signal, but this time the modulation frequency is 2 omega c instead of omega c. When we will be using the low pass filter, as you know, the low pass filter passes all the frequency components less than the omega c frequency. So this component will be passed and this will be blocked. So we will be left with the original message and thus demodulation is done. Now let's analyze this signal in frequency domain. So what will be the Fourier transform of this whole portion? This is half empty, and as we have said in the previous slide that this was the frequency spectrum of the original message. So simply half empty will result in half m omega in the frequency domain. Now what is the case for empty cos 2 omega ct? One thing to remember, when you are multiplying a signal with a cos wave in the frequency domain, the thing that happens is the frequency spectrum of the original message signal is transformed to the positive and negative values of the carrier frequency or the frequency of the cos wave. As you can see, in this case, we were multiplying by cos omega ct. So original message spectrum m omega was divided into two parts. First one was at omega c center frequency and the next one was at minus omega c center frequency. But in this case, mt is multiplied by cos 2 omega ct. So now the spectrum will be shifted to 2 omega c center frequency and minus 2 omega c center frequency. So this is the portion of the message spectrum which is shifted to 2 omega c center frequency, and this is the portion of the message which is shifted to minus 2 omega c center frequency. And this is our original message spectrum which is half m omega. Now let's take a look at the amplitude of each of these spectrums. First of all, this is half m omega. So obviously the amplitude of this part will be half of the original amplitude. As the original amplitude was 2a, the amplitude of this portion will be just a. Now we know that whenever we multiply a signal with cos wave, the original message is not only shifted to the positive and negative values of cos frequency, but also the amplitude of each of the spectrum is half of the original. Now in this case, the message was not empty, it was half empty. If in the case of m omega, the amplitude is 2a, in the case of half m omega, the amplitude will be a. And as this signal is multiplied by cos 2 omega ct, so the resulting spectrums will have 1/4 of the original message amplitude, that is a by 2. Now here is a representation of the low pass filter we are using. The low pass filter only passes the components less than omega c frequency. So these two high frequency spectral components will be blocked and the resulting signal will be like this. This is the original message. Now let's talk more about our Dsbsc modulators. First one is multiplier modulator. We have already talked about the basics of this. A multiplier block is used and two input signals are simply the message signal and the carrier signal, and the output signal is the modulated signal. But the problem is, I have mentioned in my previous lectures of Dsbc that using multiplier blocks are very expensive and complex to implement. So we will be using alternative modulators. Let's talk about another type of modulator, which is non-linear modulator. The block diagram may seem a bit intimidating, but let me explain what is happening here. As usual, there are two inputs. First one is message mt, another one is carrier or cos omega ct. Then there are two summar blocks. This summar block sums the two input it receives. The first one is mt, the next one is cos omega ct. So x1t will be cos omega ct plus mt. This summar block does similar thing, but one difference is, in this case, the mt will be negated from the cos omega ct, and this is demonstrated by the minus sign in this part. So x2t will be cos omega ct minus mt. Then comes to non-linear blocks. The non-linear blocks simply introduce non-linearity in the signal. That means previously we were dealing with xt, now we will deal with a non-linear equation of xt. The characteristics of non-linear element can be anything. In our non-linear modulator circuit, the particular non-linear block we are using will be this. If the input signal is xt, then the output signal yt will be some constant a multiplied by the square of the input x square t plus another constant b multiplied by the input signal xt. The input to this nonlinear block is x1t and the output is y1t. The y1t will be ax1 square t plus bx1t. Now if we input the value of x1t in this equation, the equation looks like this: a into cos omega ct plus mt whole square plus b into cos omega ct plus mt. In a similar manner, this nonlinear block takes x to t as input and the output is y to t. The equation of y to t will be ax2 square t plus bx to t, and similarly if we put the values of x2, then the equation will be a cos omega ct minus mt whole square plus b cos omega ct minus mt. Then there is another summing block which actually acts as a subtractor and subtracts y1t and subtracts y2t from y1t, and the resulting signal is zt. So zt is y1t minus y2t. So basically this signal minus this signal. We can divide it into two parts. At first we are taking a as common from these two parts. So a multiplied by cos omega ct plus mt whole square minus cos omega ct minus mt whole square plus the subtraction of this part. The subtraction of this part from this part will be simply 2bmt, because when we are subtracting this from this, the cos omega ct will be negated, and as there are two empties, so the result will be 2bmt. Now if we consider this as a and this as b, then this is actually a plus b whole square and this is actually a minus b whole square. If we recall from the basic algebra that a plus b whole square minus a minus b whole square is actually 4ab, so the resulting signal zt will be actually 4 into amt cos omega ct plus 2bmt. You can see there is a bandpass filter which actually passes the component having the frequency closer to omega c, so only this component will be passed and this low frequency component will be blocked. As you can see, there our message multiplied by the carrier, so this is the modulated signal. It has some coefficient in front of it, but that is not a concern. Now let's talk about some features of this nonlinear modulator. The signal, which is the input to the bandpass filter, doesn't have the carrier component itself. You can see there are two parts of it. The one is the modulated carrier, another one is the message, but there is no carrier component. If a modulator circuit suppresses either of the carrier or the message, it is called a single balanced modulator. So in this case, the carrier is suppressed and the message is present in the input to the bandpass filter, so we can call it the single balanced modulator for the carrier. Then comes switching modulators. Basically, we know the basic principles of switching modulator from our previous discussion of Dsbc. In the Dsbc modulation and demodulation technique, we use a system where we are using a signal Wt for modulating or demodulating a signal. This is basically the same thing. We know that we can easily create a Dsbsc modulated signal by multiplying the message and the carrier. But the multiplication is complex, so we replace the multiplication operation by simply switching operation. That is why this type of modulators are called switching modulators. And this multiplication can be achieved by multiplying mt by any periodic signal phi t of the fundamental frequency omega c. So in our case, phi t will be Wt. Wt is indeed a periodic signal which has the fundamental frequency of omega c. As you can see, in the Fourier series expansion of Wt, there are components having odd multiples of omega c. Cos omega ct minus 1 by 3 cos 3 omega ct plus 1 by 5 cos 5 omega ct. When the message signal is essentially multiplied by Wt, you can see each of these components are getting multiplied by mt. So when you are multiplying mt with a cos wave of omega c frequency, you know the spectrum will be shifted to plus omega c and minus omega c. Then when you are multiplying it with cos 3 omega ct, the spectrum will now be shifted to 3 omega c and minus 3 omega c frequency, and so on. So we will have frequency components at omega c, 3 omega c, 5 omega c, 7 omega c, and all of the odd multiples of omega c center frequency. Then when we will pass it through a bandpass filter of omega c center frequency, then all of these components which have higher frequencies compared to omega c will be blocked, and also the lower frequency components will be blocked. So the result will be only this part, 2 by pi mt cos omega c. There is a visual demonstration of it. This is the original message signal and this is the frequency spectrum of it. Then when we will multiply this message with this Wt, simply the multiplication will be something like this. When the Wt is 1, it will pass the message. When the Wt is 0, the output is 0 correspondingly. This pattern goes on. And as you can see from this equation, this spectrum will now be repeated at omega c, 3 omega c, 5 omega c, 7 omega c, etc. frequencies. You can also see a pattern that as we are increasing the frequency, the height of the spectrum is also decreasing. In the case of cos omega c, it is only 2 by pi, but in the case of cos 3 omega c, it is 2 by pi multiplied by 1 by 3, so it is 1/3 of this component, and it decreases gradually. And then when we will pass this through the bandpass filter, only the omega c component is passed and all other components are blocked. Now let's use this technique and develop some circuits. This is the first circuit, which is called Diode Bridge Modulator. We can use it in two fashions, but the core component of this Diode Bridge Modulator is this circuit. This source in the middle is the carrier component, A cos omega ct. A can be simply 1, so it is essentially cos omega ct. When the polarity of this source is something like this, plus in this side and minus in this side, then all the 4 diodes will be forward biased. You can see this is positive, so this diode is forward biased, this diode is forward biased, this is negative, so this diode is also forward biased, this is also forward biased. So when all the 4 diodes are conducting, if we assume ideal diode model, then there is absolutely no voltage drop in this path. So essentially C and D are at same voltage level. So this path is actually short circuited. And when the polarity gets reversed, now all the diodes are in the reverse bias and A and B is actually open circuit. So imagine this circuit in this place. The input is empty, then it is followed by this diode bridge and then the bandpass filter. As I have mentioned, when all the 4 diodes will be conducting, this will be a short circuit and the message will be passed. At that time, the message will be multiplied by 1. But when this source reverses its polarity, then all the 4 diodes will be reverse biased and A and B will be open circuited. So no component will be passed. That means empty is multiplied by 0. This is actually the same thing as this. At some times, empty is multiplied by 1. At another times, empty is multiplied by 0. This goes on and on. I have mentioned in the previous lecture of Dsbc that the switching operation of the diode is controlled by the carrier component and not the message. The same explanation holds true for this too. We can use this circuit in this fashion too, as the shunt bridge. In this case, when all the 4 diodes are conducting, A and B is short circuited, then all the message will be passed to this path and the input to bandpass filter will be essentially 0. But when this source reverses its polarity, then all the diodes will be in reverse bias and A and B will be open circuited. Then the message will be passed to the bandpass filter and essentially the message is multiplied by 1. So these two circuits have the same working principle. The only difference is, in this case, we are using the short circuit. In this case, the message is passed when A and B is short circuited, and in this case, the message is passed when A and B are open circuited. This will work as a single balanced modulator because in the multiplication of MT and WT, you can see there is the message component itself, but no carrier component. That means the carrier component is suppressed, and thus these two circuits work as single balanced modulator for the carrier. By a transformer, the primary of this transformer is connected to the message, and the secondary is this. This is the diode bridge. We are using a center tap transformer, and the input is the carrier. Now consider the carrier in this polarity, plus is on this side and minus on this side. In that case, diode D1 and D3 conducts because they are on forward bias, but D2 and D4 doesn't conduct because they are on reverse bias. So in this case, the message is passed to the bandpass filter without unchanged. That means the message is essentially multiplied by 1. But when this carrier reverses its polarity, then this side is minus and this side is plus. That means D1 and D3 gets reverse biased and D2 and D4 are forward biased. In that case, the message will be transmitted in this fashion. The signal from this point will be transmitted in this path, and the signal from this point will be transmitted in this path. So essentially, the VIT, or the input to the bandpass filter, will be the reverse of the message. That essentially means the message is multiplied by -1. So if we consider this as our W0T, or the multiplying signal, that is 1 for this polarity and -1 for the reverse polarity. So now the multiplying signal is actually different from WT. You can see in the case of WT it was 1 0 1 0 1 0 and the repetition of this pattern, but in this case W0T is actually 1 minus 1 1 minus 1 1 minus 1 and the repetition of this pattern. There are similarities between these two signals, and the Fourier series is also similar. You can see there are also all the odd multiple components of the fundamental frequency omega c, but there is no DC component. You can remember in the Fourier series expansion of WT there was a DC component, but in the case of the Fourier series expansion of W0T there is no DC component. So when we will multiply this message with this signal, the output will be something like this, because as you can see, when the input is 1, this is the shape of the message. When the W0T is -1, the message shape gets shifted to the negative side, and this goes on and on. This circuit is actually a double balanced modulator circuit, because in the multiplication, as you can see, when we will multiply this W0T with MT, there are no individual message or carrier components. That means this diode bridge circuit essentially blocks both message and carrier. That means this is a double balanced modulator for both message and carrier. This signal will be passed through the bandpass filter. The bandpass filter will block all the components higher than omega c frequency, and these components will be blocked. So the output will be 4 by pi MT cos omega ct. This is our modulated signal. It is the message multiplied by the carrier, and of course there is a coefficient in front, but that doesn't matter. This was the end of our discussion on Dsbc. In our next discussion, we will talk about another type of amplitude modulation, that is single sideband amplitude modulation. Thank you.